Got a lot of different things to talk about. Nothing complicated, though. Everything's pretty straightforward. I want to get back into the spectrum of angle modulated signals and go over homework set number 5, because that's going to be the basis for the quiz on Thursday. So go ahead and pass out those Bessel function sheets from the book. This sheet that's coming around is not a stellar piece of graphic work. All it is scans of what's exactly in the book. But when you take the quiz on Thursday, and when you take the next exam, when you take the final, it'll be handy to have those on the page. You know, in today's computer age, I don't use tables like that anymore. But when you take exams in a college course, what are you going to do? I mean, you might have Bessel functions on your calculator. As a matter of fact, I think the TI-89 has them, but I'd rather you just use the concise, I'll design problems to use that table, or those tables. The other thing I want to do first off, though, is talk a little bit about the quiz. Not that it needs a lot of explanation, because the average was fairly good, but I'd like to at least go through some of the other details associated with frequency converters and such that we really haven't. Now that we have an example problem, sort of a practical one out there, cover through that. Which also reminds me, if I have the web browser functioning here, I added some info on this histogram yesterday, as this Friday is the last day to drop, and I'm not making any suggestions for anybody. I'm just making sure that I don't entrap anybody and you know what's going on. I added in the quiz number 7 scores. I then compiled the quiz average based on dropping the lowest score. So that's the histogram of the quiz scores as it stands, with the lowest one dropped. This is the histogram of the first exam. So that's as much official information as we have right now on the semester. The projects are sitting on my desk. I worked all last week on a subcontract, so I didn't get them graded, but you can just take a look at that if you're interested.
Is the project 10% of your grade?
It's whatever the syllabus said, which if we want to review that, we can go look at that.
I'll look it up.
I think you're right, though.
Yeah, the projects are 20% of the credit.
Of course, just there it is. Yeah, so there'll be 2 projects, and that one's worth 10% then. So let's take a little bit more of a look at this quiz, which I messed up on kind of badly because I wanted to make it look as realistic as possible. So there's 2 versions of the quiz, and this is now posted on the website too. I had intended to switch the intermediate frequency to 160 megahertz because that would give better image rejection. And I changed it in the block diagram, but I left it in the text. So that made, remember when a lot of you left here, I had announced that, and then I realized I messed that up. So there's 2 different solutions. The 160 is the first page here, and the 70 is on the second page. So if I scan down through here, this is the same problem reworked with 70. But then I've got a third page that I'm going to go into some detailed discussion, things that were not necessary in answering Part D, but just some considerations I decided to write up last week. So this is the real Wi-Fi at 2.4 gigahertz, and interleaved against the back of this is actually Bluetooth. And Bluetooth Low Energy, I believe, occupies this same band. So you can see, you might ask the question, why are they overlapping, or how can they overlap? They can't really overlap, right, in a practical setting. They have to be distinct from each other. So if you've got You know, in your house, you might have a router where you have to set it. The first router that I had in my house, you had to manually declare what channel you wanted to put your router on. Nowadays, the newer one that I have at my house automatically selects, and I bet some of you have that type also. Has anybody ever set a wireless router up? If they're to know?
I've never seen that though.
The layout?
Setting up the channel?
No. Well, the consumer doesn't normally need to know that, but in the very first one that I bought, it was a requirement. You had to set it up.
Most of America getting by with how you select the channel they want.
You can't see what?
Like if a regular American grabbed it instead of
An engineer?
engineer.
Well, they can read the instructions manual a little bit, but they can say you can be on channel 1, channel 2, channel 3, or whatever. I think the first one had some simple instructions which just said leave it on the default if you don't know anything. But if you leave it on the default and everybody else leaves it on the default, then you'd have a lot of local interference. So what was interesting about this, the block diagram that I gave you came from an RF integrated circuit paper as I was scanning around the internet looking for something realistic. So this was an IC design, and that's the reason why the block diagram shows the image reject filter and the SAW filter drawn off that rectangle. So in the day when this chip was designed, the filters have to be off chip. You know, in some RF CMOS designs, you can integrate filters onto the silicon itself, but SAW filter is definitely going to be off chip, and an image reject filter more than likely would be off chip, but there's other types of designs out there. So this one takes it down to an IF at some frequency, and I chose 160 or 70, and then it takes it down to baseband with the second local oscillator, and that wasn't part of the problem, but this local oscillator in here would just sit with its LO2 right at very close to the IF frequency. It would probably take it down to within a few kilohertz or tens of kilohertz, right down to baseband. And baseband means taking the spectrum and centering it right around 0 or close to 0. There's offsets and other things that show up at DC, so sometimes they take the signal down very close to baseband, but not quite on it. And that's what the second local oscillator would do. Then the low-pass filter can recover just the information, and then in this case it was going to go through a variable gain amplifier. That's what the VGA stands for. That can be programmable based on signal strength to keep the signal at a proper level for going into the A to D converter. Not really a subject of this class. This is actually a subject that I've wanted to teach a class on for many years, on RF integrated circuits and communications, kind of how that piece of the puzzle goes together. Why do you suppose you'd want that VGA in front of the A to D converter? Is anybody, it's not part of this class, but just reasoning out from a signals standpoint. Suppose you only have an 8-bit converter, not a really high resolution converter. So if the signal is too tiny and it's only got to spread itself over 8 bits, which is 256 levels, and it's, say, only a quarter of that, then you're only getting an effective number of bits of 4. You get lots of quantization error. So the VGA can be used to keep the signal dynamic range as closely matched to the converter's dynamic range. If you've never thought about that, it's something that you may bump into someday. It's not magic. Your analog doesn't become digital as perfect as you'd think without having some means of matching the dynamic ranges up. That's one of the complaints that people had about the early CD player, was that it was only 16 bits. It still is a 16-bit standard. And the dynamic range, people contended, was not good enough for classical music, which would have very loud passages and very soft passages. And they contended that the dynamic range needed to be greater, but in vinyl recordings back in that era, their dynamic range could be acceptable, but there was always background noise just because of the analog pickup mechanism of having this groove that the needle was in and moved back and forth, and it would pick up noise because there would be dust and dirt on the recording. But you guys are too young to appreciate that, I guess. Actually, my son asked a question of my wife and I about a vinyl recording because I have a lot of them at home still. I don't listen to them, but I have them. He said, how could you choose a different track? Well, it wasn't all that hard to do because all I had to do was move the needle as the turntable was turning your vinyl LP. You just moved it over to a little gap that you could see and drop it down, and it would be cued right in between two tracks of music and start playing the next one. Now, my wife and I, that's just a natural thing. For most of you, that's like, what? What is that? That seems so crude, but it works, and it worked well because they had a gap in there. As I recall, I think fancy turntables could actually sense where that gap was, and you could just say track 1, 2, 3, or 4, and it would hunt across, reflect off of that surface where there were no grooves between tracks, and drop down and start playing. It does seem really crude, though, doesn't it? 8-track tapes and cassette tapes seem pretty crude by today's standards as well. So calculating these frequencies, either high side tuning or low side tuning, I think that is pretty straightforward. Either add 160 megahertz or subtract. So your two options. Image frequencies have to be twice again the IF frequency above, or twice again the IF frequency below the desired frequency. So those two potential images that can also convert. And remember, image frequencies are specific to high side or low side tuning. Part C was what would be the required bandwidth of the IF bandpass filter. Well, you look at the bandwidth of any one channel, and it's 22 megahertz. So that would be sufficient. You wouldn't really want it any wider than that because then you would be letting energy in from an adjacent channel. So then the next question, which was kind of open-ended, what's the purpose and the requirements of the image reject filter? Well, it's to reject the image frequency, which either is 2 times FIF above or 2 times FIF below the signal of interest. And it needs to have a bandwidth of at least 22 megahertz so that it can pass the signal of interest, but it also has to be no more than the distance the image is away minus the half the bandwidth of the signal. And I didn't have enough space to throw that in. I just wrote down 618 megahertz, but on this next page over here I was writing down I drew a picture of what I was talking about. If this was the signal you wanted to receive, and that blue dashed line represents this image reject filter, and if you're using high side tuning, the image would be sitting right up here at 2 times FIF away from the desired signal, and if the signal occupies a bandwidth that sits effectively 11 megahertz below the carrier, if it's another Wi-Fi signal, let's say, or a like type signal, then your filter has to be rejecting the lower band edge of that signal, is where I came up with that. But it turns out that that's not really even the exact requirement because the Wi-Fi band is not that wide. The Wi-Fi band does not go up that high. There's some other unlicensed spectrum is using that band of frequencies. So then the question came to my mind is, if I'm using a 70 megahertz IF or a 160 megahertz IF, can I get away with a single image reject filter that can just ensure that I get Wi-Fi signals and I can reject images all at the same time? And it turns out that the answer to that question is yes, because the total band of the Wi-Fi signals is smaller, and here's the calculation for that. The way I got that number was I went up to the picture up here and I said, okay, there's my lowest frequency carrier, there's my highest, but then I need to drop 11 megahertz below and 11 megahertz above that. So that got me my total RF bandwidth. Does that make sense? You see that? Have to have 11 sitting in here and 11 sitting in here, and then it's the total delta from 2412 up to 2484, which is the 94. And, well, it's not the 94, it's the 94 less 22, but when I throw that in there, it comes out to be a total of 94, which is what I have in this picture right here. But then the next consideration I gave was if I put my IF filter at 70 megahertz, so I can get this image reject filter is not a problem to build that one. But then I said if I put my IF filter at 70 megahertz and I need to have a 22 megahertz bandwidth, the fractional bandwidth that I need for that filter is 31%, and that is actually a pretty large fractional bandwidth for an IF filter that would have really steep skirts and have that wide of a bandwidth relative to 70. But if I shift up to 160 megahertz, then the fraction is only 13.75%. So that's more reasonable, and the reason why I changed the problem is because just before I before I printed the problem, I went online and did a quick search and found 160 megahertz SAW filter, and this is part of the data sheet for it, the 22 megahertz bandwidth. I don't know if you can see in here, but this filter it's kind of faded out on here, but it's extremely sharp. It just looks like a brick wall sitting there centered right at 160. And I had to think about this for a while and say, why did they make this 22 megahertz filter? Was it for a Wi-Fi application? Probably not, because most Wi-Fi receivers get by with other cheaper solutions. But then I thought maybe there's another application, and then it occurred to me that GPS would use 22 megahertz as well for the wideband secure part of GPS, because it chips at, the chipping rate is 10.23 megachips per second, whereas the commercial one is 1.023 megachips per second. So they might be easily available, but I'm not sure if that entirely makes sense either, since this came from a Chinese company and the military applications would be for the US only. You can go think about that. I don't think they're supplying parts for our secure communication stuff, but so maybe it is for Wi-Fi after all. Who knows exactly? These are types of things, though, that you end up doing when you're working on a project in industry. You're going out and scoping parts. I did find the fractional bandwidth through the image reject, and that's 3.83%. And that's controlled by the band itself. It can't do anything about that. You can't move the IF around to change that. That's a function of the center of the Wi-Fi band. That's a fairly narrow percent. But you'd probably make that a little bit wider, because 94, the images with the 70 megahertz are 250 megahertz away, or they're 618 away with the 160, or you can have bandwidths up to 618. So that 94 megahertz is not a strict requirement. You can get by with a much wider bandwidth filter and not have to push the fractional bandwidth down.
So what does the fractional bandwidth tell you?
It tells you the realizability of the filter. If you're trying, and in electronics somewhere, don't you build something with a resonator, a tank circuit, and sweep it, like with an L and a C? I know you do it in the comm lab, but there's a problem with trying to build a really when you build a tank circuit with an L and a C in parallel, you don't just have L and C, you've generally got losses in there, so you've got an equivalent shunt resistor across there. And that's due to the loss in the inductor, usually due to the metal loss. And then the capacitor has a dielectric loss as well. So if it was perfect L and C, it would be a very sharp pass band because the key would be very high because R is essentially 0, but or infinite, I mean. But when you have the R present, then the bandwidth spreads out. And when you have resonators that have a lower Q because the R is present, then trying to build a narrow or fractional bandwidth filter becomes very difficult. You can't really get there. If you try to do it, you end up with a filter that has a lot of insertion loss as well. And when you have insertion loss, then the passband signal gets attenuated. And if it's right at the front end of the receiver where the signal is weak, that pushes the signal down into the noise floor, that attenuation, and then that ruins the sensitivity of the receiver, if that makes sense. I mean, you have a weak signal, and if you push it down into the noise, you can't get it back again because your filter has got too much attenuation. So the fractional bandwidth has to be watched, and the material has to be watched as well. This SAW filter doesn't have a 0 insertion loss, but it's at the IF level. I think it shows it as being an insertion loss of 28 dB. That would be absolutely unacceptable at the front end of a receiver. But at an intermediate frequency where you can gain the signal up above the noise floor, then that's okay. We'll talk about noise figure later at the very end of the semester when we go to Appendix A. So I just thought that might be interesting. This is where comm theory and RF systems and microwave circuits and stuff sort of are butted right against each other. So if a person is working in this domain, they're kind of got one foot in the microwave RF circuit side and one foot in the comm side. Exactly. I mean, they're right at the dividing line. So you've got certain types of engineers will have skills in both sides, just like DSP algorithm developers will be good systems analyst people, and they'll also have another foot in the FPGA implementation side of things. That's why you have a diversity of courses you get to take, but you can't major in everything because you have no depth. You have to have some certain selected majors and then your distant minors, I guess. That won't become apparent until you start working, though. And if you end up picking a job where you don't have the strengths that you wanted, you'll come back to graduate school and take some other course. That's usually the way it works. You can't predict, though, because you don't know necessarily where that first job is going to be. Okay, moving back to where we had left off from last 2 weeks ago. We're looking at the spectrum of an angle modulated signal, and we were focusing on the case where the phase deviation was sinusoidal, and that bumped us into wanting to get the spectrum of this signal. And because it's periodic, we went over and said, okay, we need to get a Fourier series representation for that. And the Fourier series representation involves coefficients that are the Jn Bessel functions, and that's a special function, like I said. And I think you guys mostly said that you hadn't seen it before, maybe bumped into it in differential equations, maybe it was mentioned. It's a special function that I handed out the table for it. There's recurrence relationships to go back and forth. There's symmetry properties, and so on. So these are the primary properties that we need to know about. Beta is known as the modulation index. So this picture is what is on the handout. This is a variation of also what's in the book, and on the handout it tells you where the zeros of the Bessel function occur. So for example, this 2.4048 is this point right here. And then it occurs at other locations, and there's zeros of the other Bessel functions. This happens to be something that you do in the lab just as an experiment to verify that you're understanding sinusoidal FM. When you put the Bessel function coefficients back inside, in other words, I modified the notes slightly today because I felt like that was missing. We expanded that e to the j beta sine omega mt into the Fourier series, and that became this representation here. Plug that back in, then take the real part. So now you've got it in terms of cosines. J and beta are the coefficients. AC is the amplitude on the carrier. And then the harmonics are occurring at n omega m relative to the carrier frequency. So when you plot out, say, the magnitude, this is what the Bessel function spectrum looks like for sinusoidal FM. It's got a lot of sidebands on it, depending upon what the value of beta is. As long as beta is greater than 0, you've got sidebands that just start to grow bigger and bigger and expand the spectrum out about the carrier frequency. And beta is the key for getting that. If it's phase modulation, beta sine omega mt is exactly equivalent to the phase modulator, where we had this form. We had Kp times A. So in a phase modulator, beta is equal to the phase modulator's modulation index, so many radians per volt, times the peak amplitude of the message would be A. So that would give us a beta value. If it's FM and we're putting in a sinusoidal FM type message, then we have to integrate it first. So if the message was of the form, I didn't have it written in here for whatever reason, A cosine omega mt, if that's your message, throw that in the integrator that's part of the FM modulator. Always remember that because of the way frequency deviation and phase deviation are related, frequency deviation was the derivative of the phase deviation. So to go back to phase, you have to integrate. So integrate the frequency deviation to get phase deviation, and that cosine becomes a sine, and then the 2 pi omega m pops out, and then there's a 2 pi in the numerator that's part of kf. If you remember back before break, kf was 2 pi times fd. Kf was the deviation constant for FM in terms of radians per second, whereas the more common way of working with it is 2 pi times fd, where fd is the deviation constant in terms of hertz per volt. So kf would be radians per second per volt, and fd is hertz per volt. So the 2 pi's cancel, and beta ends up being fd, the deviation constant of the modulator, over the modulation tone frequency times the amplitude A. We're going to look at voltage-controlled oscillator concepts here in a second, but FD, we'll see, is the sensitivity of a VCO, is what it comes down to, voltage-controlled oscillator. So when beta is very small, the Bessel functions are barely activating. We can go back up here to this picture. When beta is really tiny, so you were slicing down there, beta much less than 1. The J0, which is the strength of the carrier, is pretty much 1, and then the other Bessel functions are just starting to grow, but they all start from 0, so they're very tiny at that point. That's what we call the narrowband case, and that we talked about earlier. When beta was much less than 1, then we could use a power series expansion, and the dominant term is just the first sideband. So this would constitute narrowband, because all we have of any significance is the first sideband pair. But I'm somewhat lying to you, because this is a linear axis. Those of you in particular that have been in the lab using the spectrum analyzer with the dB axes know that there's actually plenty of other things lurking down there, because the dynamic range capability you get with a log scale, right? So they're actually there, but they might be down 30, 40 dB, and so they're not all that significant.
Those first pair probably aren't?
The first pair are significant, the rest are not,
Right.
though. Yeah. And as beta gets bigger, they get bigger. So I have a little animation here in Mathematica that I think we looked at, and I'm going to look at it again. And I'm going to ask you to refer to your table here too, just so we can play sort of a little game of sorts. Okay, beta 0, nothing but the carrier. Think of this as being centered on the carrier. I've actually got it as F minus FC normalized by FM. So the first pair of sidebands is always going to occur at 1 and minus 1. So as I increase beta, I could say, I could just plug a number in here. I was just looking at 0.2. So there's 0.2. That was the beta value that I had in that picture on the notes. You can actually see if I change the vertical scale here, there is, even on a linear scale, there is a second set of sidebands. But if I get the carrier in here, which is almost an amplitude of 1, then you can see that the second pair of sidebands is quite small.
So for this, the handout you gave us, this table 3.2, that's going to give you it's telling you what the amplitude spectrum is going to be?
Exactly. Yeah. That's a good question. I put that up here for a reason, but I didn't load it, so let me go load that up. I'm putting in beta equals 0.2, so if we were zooming in on this table entry right here, we're in this column. So the carrier has got a strength of 0.99. The upper and lower sidebands have a strength of 0.1. And then the next pair of sidebands is 0.005. Does everybody follow that?
And then is it just that beyond that it's so small that you don't really...
He didn't list it beyond that, yeah. And these double underlines and single underlines we're going to talk about a little bit later. There's a significance to those too. Does everybody follow that though? Okay, so back to this guy. So now if I increase beta, and it's kind of sensitive here because I have, notice what's happening. The carrier is dropping. So as I increase beta, the carrier is going to go through 0 right in here, and it's actually, what was that number? Look on the top section of your table. The carrier goes to 0 the first time when beta is equal to. So there it is exactly. Suppose I wanted to just call out a value you want to verify just to see if the plot comes out right. What's another sideband you'd like to see go to 0 either the first or the second time from the chart?
8317.
Okay, 8.317.
3.8.
Okay. Is that right?
8317.
Okay, so that's putting the next pair of sidebands to 0. And for those of you that didn't follow that, we'll go up here to this table. They're basically calling out that guy right there. I mean, it's 0 when beta is 0, but that's not too interesting because there's no modulation then. It's turned off. But the first value for beta not equal to 0, that the first pair goes to 0, is at 3.8317.
Dr. Wood,
Yeah?
how come the third pair and the fifth pair are not listed in there? Like n equals 3 and then equals 5?
I don't know why he did that. Actually, he doesn't even have them plotted in here.
Exactly.
Have to ask Dr. Ziemer that question. But watch what happens if I increase beta, though. I mean, they definitely. There's the second. There's the third, and it's all happening. I just don't know what those numbers are. The zeros of that Bessel function. It's somewhere right about in here. I just can't quite set it fine enough.
Right, for the third one.
Yeah.
There it is.
There it is again. That's the second time it's gone to 0. It went to 0 back over there too. It just keeps going, and I set this up with not an automated scale, but I could change that, pull this up, because the energy is now spreading. And it just spreads, as beta goes up bigger and bigger, it just occupies more and more bandwidth. And I called this the suspension bridge, or at least that's what I say it looks like. And when you're on the spectrum analyzer, you see this only in the logarithmic scale, so it doesn't look quite the same as this, unless you put it on the linear scale. But what we're going to be talking about here next is what defines the bandwidth, and we want to say that this signal occupies a certain band of frequencies about the carrier. Remember, for double sideband in AM, it was always just twice the message bandwidth. Now we're putting in a message that's at omega m, which is normalized to 1, so the message bandwidth is just 2 times FM, which is way in here, but the bandwidth of this signal with the large deviation constant, which I'm going to define, is spread it way, way out. And broadcast FM does this exact thing. So it spreads it way out. And from what we were talking about in Project 1, we were trying to be efficient with the use of spectrum. This is very inefficient. This is spreading things out a lot. But there's a benefit of doing that if you've got the spectral resources, and we do it all the time. We certainly do it in cellular telephony. We do the same thing. So let's go back to the notes, unless somebody has another question. I guess the other thing I'll point this out when I go look at one of the homework problems. Does anybody have any questions?
Back to the handout, I'm having a hard time figuring out what the graph in the middle is supposed to help us with.
This?
Yeah.
I just threw it in there because it's also in the book. It's just a visual of what the functions are doing, how they're...
You can see the models pattern.
Yeah, you can see roughly.
This is like for all different families of data, and then specifically what their sideband amplifications are, essentially.
Well, yeah, as beta goes up, you're going along the horizontal axes, and then I'm just overlaying the plot of the different Bessel functions. The J0 sets the amplitude of the carrier. The J1 sets the strength of the first pair. J2 the second pair, and so on, out like that. That's all it is.
So for one particular beta, you look at the value of each of those curves.
Yeah, you just slice down. That's like, at beta equals.
You can figure out your spectrum.
Yep.
Okay.
Of course, as was pointed out, 3 and 5 are missing. I think Dr. Ziemer probably decided not to draw all of them in because it was going to get too cluttered. Decided to skip some of them. But this table down here doesn't skip any values. It just cuts off when they get really tiny.
Okay.
So you've got, all of them in here.
Because when you increase your N, it takes a higher beta for it to get
To be activated.
zero.
Yeah, and you can see that in this plot. How as the Bessel function order goes up, it's slower to activate. Like J6 doesn't start coming up to any significance until beta is 3, between 3 and 4, and then as higher orders of Bessel functions will activate even slower. And we can, the other thing that I didn't point out is you can actually use this recursion if you wanted to. You can use this guy. This is how you can get to a higher order. If you wanted to get to J10, you'd need J9 and J8. So if you only had values up to J5, let's say, you'd have to bootstrap yourself from 5 to 6, and then from 6 to 7. Yeah, and do it with the recurrence. And that's actually the way the computer works. The computer doesn't have a catalog pre-stored of all the Bessel functions. It has a very high precision table for J0 and J1, and then it uses this recurrence relationship to take you up to the higher orders.
Now, with this given us the negative values, like would those invert your phase?
Beta is always positive, but if you wanted to get the negative n values, then you have these two relationships here for negative n, for negative Bessel function orders. Then if it's even index, then the sign doesn't flip. If it's an odd index, then the sign flips. So it's like the spectral line has got the same magnitude, but it's 180 degrees phase shifted because it's got a negative phase. Or positive 180. I mean, it's the same idea. Okay, so let's look at an example where I'm taking a VCO as an FM modulator, voltage controlled oscillator, which I was thinking you got introduced to in electronics, but maybe you have or maybe you haven't. It used to be. So I'm old-fashioned. This was written when I knew for sure that happened. I don't know if Dr. Wong does any things with VCOs or not.
Which bus?
Electronics 2.
Not so far.
I don't think we do.
Doesn't the 555 timer have a means of controlling the frequency by a voltage pin?
You're talking about the lecture, not the lab?
I'm talking about any one, either one. Isn't it possible to control the frequency of a 555 with a pin, a voltage?
We never.
You never saw the 555 either?
Is that like an Allen 5?
Yeah.
We might.
Okay. That's like one of the oldest analog parts out there, but it's a famous one, just like the 741 op amp is. The guy that invented the 555 timer just passed away recently. I mean, it was in the electronics news. I saw it. It's like the guy that invented it because he was famous for it. It's, you think technology comes and goes rather rapidly, but certain things, when they came into being, some things have lasted, for many, many, many years, and that's one of them. You guys use the 741 op amps, right? I've often wondered why do you keep using that same old op amp? Because there's better ones out there. But it's a classic, so it stays around. Okay, in the COM lab, though, you will be looking at the function generator as a VCO. There's a port on the back of one of the types of function generators we have in the COM lab that can turn it into a VCO. So basically, you program up on the front panel that you want it at some center frequency, say 10 megahertz, and then you can go apply a signal to the back panel of that function generator, and you can deviate its frequency about FC. So you can apply a message signal, another sinusoid, a DC bias, whatever. So you can tune the frequency above and below the quiescent frequency set by the front panel. It's the sensitivity of that control port that makes it definable as a voltage-controlled oscillator. So it's got some sensitivity, and I've got it written here as megahertz per volt. It might be kilohertz per volt, but you're going to discover what that is in the COM lab experiment that deals with this. If you bought a VCO off the shelf, or if one was designed on chip in an RF CMOS or whatever, you would have some characterization, and generally you want to see how linear it is as you vary the voltage up and down about some quiescent point. You'd want to see how linear it is, so you generally plot some data points, and then you do a curve fit, and then you do a first order polynomial, so you get the slope of the line. That is your FD, and that's exactly the modulator constant we were just talking about for sinusoidal FM modulation. So FD along with FM, that and the amplitude forms beta, remember? So beta is FD over FM times the amplitude of the signal that you would feed in. And this was just an example of the 2.4048. So in the experiment, one of the things you have to do after you characterize the VCO and find out what FD is, then you want to find out what amplitude you want to apply to the input of a sinusoid to make the first pair of sidebands go to 0. So that ends up being just solving for A given FM and given FD.
Would that be the center frequency, though?
The center frequency does not enter into this calculation.
But, I'm sorry, I'm kind of lost in what the FD really represents.
The FD is the sensitivity of the voltage-controlled oscillator. It's how many volt, you apply 1 volt to the input, and it will push the frequency up by that many megahertz. If it's so many megahertz per volt, that's how sensitive it is to a frequency shift from an applied voltage. If you applied a negative 1 volt, it would shift it down. That's why I was asking if you had talked about it in electronics, because to me it's a cool little gadget, but if you haven't gotten tuned into it, we're going to use VCOs in a phase lock loop, though. It's an integral part of a phase lock loop. In Dr. Kalker's RF circuit design class in the summer, I think you build a VCO. I'm not positive. Chinche, did you take Dr. Kalker's RF circuit class in the summer? Don't you build a VCO in that class? Then you characterized its FD, probably. Okay. Some of you may take that this summer. So this is the number I came up with in this calculation. So to get the first null. So this is a legal quiz question, by the way. I mean, everything I'm talking about is related to this stuff. So what about the power in an angle modulated signal? This is an interesting calculation because it's very simple. You want to find the time averaged value of the squared value of the signal, because that's the average power. And when you do that, you square out the cosine, you get the 1/2 AC squared, which we're familiar with. That's the power in the carrier. But what about this? That's the double frequency term, and the phase modulation is sitting inside of there. But if you think about the spectrum, I'm just going to draw the one-sided spectrum. We're getting a large spike here at 1/2 AC squared, and then at 2 FC, we're getting some spectrum, whatever the shape happens to be. But as long as the bandwidth of that signal sits above DC, the average value operator is just looking to extract the DC component. If there's nothing that laps down from this signal, nothing comes down into DC, it's 0. So
Is that always the case, though, where it's nothing coming down? If you say
in a valid scenario, that's typically the way it is. Now, in the lab or in things you might do, the carrier frequency, double carrier frequency, might be low enough that it actually does have sidebands that pass through DC, and then that term is needed. But in most applications of real live RF communications, the bandwidth of the signal is narrow relative to the carrier or the double carrier, so it's just 1/2 AC squared. And that also is what makes the signal a constant envelope, because it doesn't have anything that laps down into DC. So it's very simple. The power in the angle modulated signal is 1/2 AC squared, independent of the modulation. Totally different from double sideband, totally different from AM, remember?
A lot less power.
The power can be really high. It can be kilowatts broadcasting from all the towers off of Cheyenne Mountain, but it's a constant envelope. And in satellite communications, constant envelope schemes have always been favored because the amplifiers that amplify those signals are usually what's called a Class C amplifier, or something that you want to run very close to the point of saturation. And if you've got a constant envelope signal, a clipping or an amplifier being pushed really hard to its distortion point does not destroy the signal's integrity. Rather than the information being contained in the envelope fluctuations, it's all contained inside the argument as the phasor frequency moving back and forth. So if you clip off these fluctuations and make them a constant, you don't really destroy the information. And that way you can get away with very efficient amplifiers, especially on a spacecraft which is running off of a solar and battery supply, but yet has to produce enough power to relay information back to ground. So they prefer to have amplifiers that can be very efficient, and they're running close to saturation to make the conversion of DC power to RF power as efficient as possible. You have to ask Rob about Class D. That's a different application, but that's an audio switched application. This is still an analog waveform all the way through. The next thing is the bandwidth of an angle modulated signal. Remember we were noting the suspension bridge and the fact that it just spreads out as beta gets bigger. So what is the bandwidth? Well, a good measure of bandwidth that they talk about in the book is a fractional bandwidth. In other words, to say how many sidebands do we need to include in the sinusoidal FM spectrum to capture, say, 70% or 98%. These are just two values that are tossed out here. Not that they're universal, but that's what they talk about in the book, 70% or 98%. And the single underlined is this guy, and the double underlined is the 98%. Remember that table? So in the table, that tells you, yeah, the single underline says that's how many sidebands you need to include to get 70%, and the double underline tells you to get 98% for sinusoidal FM alone. And that, of course, means both sides, so it means from symmetry both sides.
And that's 70% of the bandwidth.
70% of the total power is contained in those sidebands. We're going to see how that calculation works here in a second. So you can write notes on that and have that on that sheet if you want to. It's the way you get the total power. It's the power in the carrier plus the power in the sidebands, just like it was for AM or double sideband. So if we add up all of the sideband terms, all the Bessel functions, we'd get the total power. If we add up just K sidebands either side of the carrier, we get the fractional power. And since their magnitudes are symmetrical, this is the equation to get the fractional power. It turns out also that the 98% bandwidth is approximately the integer part of 1 plus beta. Or K, the value of K is approximately the integer part of 1 plus beta. So 1 plus 2.4048 would be the integer part of 3.4048, which would be 3, right? Does that sound right? So let's go look at the table and see if that makes sense. 2.4048 is not really on here, but it's somewhere up in between here. So this is 3 sidebands, that's 4. It's still hanging out at 3 at 2.4048, which would be stuffed in the middle here. There's not an entry for 2.4048. But for 2, you're using the carrier, first pair, second pair, and up through the third pair to get 98%.
So you just do 0.192 now?
that squared plus that squared plus that squared times 2, because you've got an upper and a lower, and then the carrier power squared, and that's that's what's in this calculation right here. See that? You're squaring the J0 value because that's the power in the carrier, and then you're taking twice times the power in the first sideband, second, third, because you've got one on each side. So for sinusoidal FM, the bandwidth is approximately 2 times the quantity beta plus 1 times FM. That's the bandwidth occupied by the signal that gives you 98% of the contained power.
So if you want the bandwidth that gives you 98% of the contained power, and you had a beta from the sheet of 0.155, so that's one of the 98% ones, you just do 0.115 plus 1.
Well, that's not the thing.
This is to calculate the bandwidth, not to calculate the power. The power calculation involves the thing up above, and there's an example of that coming up here in a second. This whole idea can be generalized for an arbitrary signal. So for arbitrary modulation, you can define what's called the peak deviation ratio, or the deviation ratio, I mean, which is the peak frequency deviation that the message pushes the carrier above or below, pushes the carrier above its nominal quiescent point, divided by the bandwidth. And that is equivalent to saying FD, the deviation constant in the modulator, times the maximum value of the message. Now you have to, the best way to visualize this peak frequency deviation is think of the VCO, like I was talking about earlier. You've got the VCO sitting here as a box. You've got a message coming into it that's driving that voltage control pin. So the VCO sits at FC with no input, but then when the signal comes along at the input and it rises to its highest value, it pushes the frequency of the oscillator up to a positive peak deviation. When the input swings negative, it pulls it back down again. So it's that positive push up is the peak frequency deviation. It shifts above FC by the peak. It shifts below FC by that same peak if it's swinging symmetrically. So that's what peak deviation means. It's a combination of the amplitude of the signal, its max value, and the deviation constant of the modulator, which I'm using the VCO analogy because that's a simple view of a FM modulator. And then you divide that by the bandwidth, and that becomes what's called the deviation ratio of peak deviation to bandwidth of the message. That takes the place of beta, because it's equivalent to beta for single tone frequency modulation, because beta, remember, was FD times A, the amount that it's going to push up, the deviation, divided by FM, which is like the bandwidth for the single tone case. So beta and D have the same role. It's just that D is for a general signal which has some bandwidth W and so on. So beta equals 2 times the quantity D plus 1 times W. And the 2 is on here for upper and lower sidebands.
So isn't the same equation as above? Why would you write it differently?
Then here?
Yeah.
That's for a single sinusoid. This is for any M of t. So you just define it differently. For an arbitrary M of t, beta doesn't really get defined because it's not a sinusoidal message. It's a general message. And Carson's rule is simply an approximation. It's not perfect by any means whatsoever. The spectrum of an angle-modulated signal is actually a study unto itself. Part of my dissertation involved playing around with developing some results for a particular type of digital modulation, but it's just more complicated. Carson's rule is just a rule of thumb, really. It says the deviation ratio plus 1 times the quantity, or that quantity times W, and then times 2 is the full bandwidth occupied by the signal. Now, another view of Carson's rule is to look at it in terms of just the peak, or the peak frequency, or the frequency deviation, I mean, all by itself, just delta f, which was maximum m of t times fd. And then what you can do, and I didn't really write it out in here, but if you look at it that way, oops, I'm just going to show you that these two equations are equivalent, and it's not that complicated. D was delta f over w, right? The bandwidth of the signal plus 1, then times w. If I just simply absorb the w inside, I will have 2 times delta f plus w, which is what I had right here. So that's just another way of looking at it. But this alternate way brings, they both have useful means of interpretation, and that's kind of what I have down here. The next comment is, when d is much less than 1, or delta f is small compared to w, then the bandwidth is essentially just 2 times w, because d is small, or delta f over w is small, and that means you're in the narrow band FM, or angle modulation scenario. It's just twice the message bandwidth, which is like double sideband. When d is much greater than 1, then the delta f dominates, and w is insignificant. So then the bandwidth looks like just 2 times the peak deviation. And this is probably what most people would think about, especially back in 2610, when you were thinking about what is the bandwidth of an FM signal. When you did one of those early experiments, you had a tone, and you stretched it up to a high frequency and stretched it down to a low frequency. So you said the bandwidth occupied by that signal must be, twice the peak deviation, 2 times delta f. But you can see that that is only valid when delta f is much greater than w, because if w is significant or comparable to delta f, then you're making there's an error in the calculation.
And w is the
bandwidth
of the original message.
Yeah.
Okay.
Or the rate at which you're pushing it back and forth. So here's an example of a single tone FM set at, I picked FM broadcast as an example, 101.1 megahertz. In FM broadcast, the deviation constant is 75 kilohertz per volt. And the idea is with broadcast FM, the peak deviation is 75 kilohertz. So I'm saying the message has got an amplitude of 1. It's going to push the carrier frequency up by 75 kilohertz, or down by 75. That makes beta 75. That makes the bandwidth occupied by the signal 1 plus beta, or 1 plus d in this case, times 1 kilohertz, and then times 2 for the double sideband part of it. So 152 kilohertz. And if I was to stretch this axis out here a little bit, what do we know about FM broadcast stations? What do you guys know from listening to the radio? Which I guess you don't do much of anymore either. I listen to Sirius on my car, but I still listen to FM radio.
Increment by like 0.2.
0.2, right?
0.2.
So the next station slot up here is 101.3, and the next one down here is 99.9. They go in the odd 100 kilohertz spacings. So have we provided enough space? If they're spaced by 200 kilohertz, there's basically a space, there's 100 kilohertz right down the middle, and then to the next center it's another 100 kilohertz. So that's okay, right? We're within the allocation. Actually, they push it up closer to 200 kilohertz because that's right to the limit. You can occupy 200 kilohertz. That's awesome bandwidth occupation compared to broadcast AM. Broadcast AM, the message bandwidth is 5 kilohertz, so it occupies 10 kilohertz. FM broadcasting is occupying 200 kilohertz of bandwidth just to listen to music. But TV occupied, ordinary old-fashioned TV occupied 4 megahertz of bandwidth. There's a lot. Very inefficient. But say it was developed back in the 40s. TV was in the 40s and 50s. So we didn't think we had anything else to use our spectrum for, so we just, it was designed and it was utilized that way. The FM broadcast actually has other subsidiary services on it, which we'll get into later, how that works. But there's HD FM. Does anybody do HD? Yeah. There's HD AM also, high quality.
They never convinced me that I needed to get a HD FM radio now.
It exists, though, because that was an add-on standard that crams another piece of information in the existing allocation digitally to give you higher fidelity, but still not force the reallocation of the frequencies. And AM is the same thing. TV, they just said, clean the slate. We're going to get rid of this old standard. We're going to put a new standard in. HD FM said we're going to keep the same standard and we're going to try to cram this extra information in there.
The broadcasting analog and digital in the same.
Yeah. And the RDS, the radio data system or service, gets broadcast there too. That's the thing that tells you what song is playing, what station name is, the other information. And there's some other stuff, and we'll talk about that a little bit later. That's under multiplexing. So this is an example of taking this spectrum right here and saying, suppose we only wanted to look at 11 kilohertz. So we just wanted to zoom in on 11 kilohertz sitting right in here. Find out what the power is contained in the 11 kilohertz centered over the carrier. So that means we're going to go up 5.5 kilohertz and down 5.5 kilohertz. So what's the total power of this signal? If the amplitude out here is 100, the total power in the carrier is 100 squared over 2, right? But now if we're going to focus in on an 11 kilohertz band, we would have to look at how many sidebands are going to get through. Well, we're putting through a signal at 1 kilohertz. FM is 1 kilohertz. So if we can go up 5.5 kilohertz with our bandwidth on either side, how many sidebands can we get in there? You got 1, 2, 3, 4, 5, right? And then we'd be sitting at 5.5, and same thing down below. So we have 5 sidebands above, 5 sidebands below, plus the carrier. And then if the filter cuts off, at 5.5 kilohertz on the high side and 5.5 on the low side, that makes the 11 kilohertz. And this is the calculation. 5,000 watts or 5 kilowatts was the total power transmitted, and then what gets through that 11 kilohertz bandwidth is this fraction.
So you don't care what's happening at the carrier frequency? You just care what's happening at the sidebands?
Now you need the carrier frequency in there to demodulate it.
Yeah,
It doesn't have a 2 on it though,
yeah,
right? There's only one of them.
Okay.
You say you need the carrier frequency to modulate or
Demodulate.
Okay.
We haven't gotten that far yet, but it's needed for demodulation.
Okay. So if you're for any of the bus functions that zero out the carrier, that's bad. No one uses those.
Yeah, you wouldn't want to do that. But that'd be tone modulation. I mean, real programming is just vacillates around. I mean, you guys that took the lab, you looked at it recently. It just sort of, it's kind of just undulating, right? When you looked at it on the spectrum analyzer, you knew there was some. Well, it's just sort of whatever the right word is for that.
Well, because where when they're talking, there's like a commercial.
Oh,
And then Bruce is actually.
Yeah, if there was a little bit of dead air where there was nobody speaking, it would just come right back to a carrier, and then it would immediately start spreading out again and just sort of undulate.
Undulate.
Where did I get that term from? I don't know. Look it up in the dictionary. It's not an X-rated term or anything like that either.
Yeah.
I think it refers to, maybe it's a biology term. I don't know. Okay, you might wonder, can two-tone FM be done exactly? I mean, I said Carson's rule gets us the spectrum approximately. Two-tone FM, I just put in a little analysis of that. You'd have to do 2 sets of Bessel functions. And when you put all that stuff together, you get a double sum. And it's quite the mess at that point, because now you've got tones at all the multiples of the underlying message tone. But this sort of analysis is actually done in one of the telemetry standards that's used by the Air Force, the system I've been working on called the AFSCN, Air Force Satellite Control Network. It relies on subcarriers, and it relies on phase modulation of the subcarriers, and these things with the Bessel functions are actually part of the math that's behind all of it. Not just invented today, but invented about 30 years ago. So this is not a new thing. This is just a snapshot of the spectrum now. Okay, I have a place for an example. This is getting into the demodulation side, which I'm going to save that for next time. What I want to do is, before we get out of here, is look at what is in the solutions to set number 5, so you can see what some of the candidates are. I've gone through a lot of the stuff already. These are just some plots of what either PM or FM looks like. These are phase modulations, though, different values of phase jumping or phase stepping. This is not really all that exciting, but it is a valid picture. So I wouldn't rate problem number 1 there as being all that high. Problem number 2, you could draw a part of this spectrum from a problem like this using the tables that I gave you. You could draw the first few sidebands based on what's in that table. So the first thing, this you're already given beta. There's not a whole lot of calculation to be done with this. But this was both magnitude and phase. And, you know, yeah, I'm not too interested in having you plot the phase spectrum now. So,
How come? Just because you can't really gather much information.
yeah,
0 or -5.
exactly. It's not really exciting. It just takes up space on the page that I wouldn't want to allocate that on a quiz, I don't think. This is a good action problem, though. This could show up on the next exam or on the quiz. This says you've got a pulse coming along, and it's a frequency pulse, so it's an FM modulator, and you're given some constants. So what does it look like in the phase domain? So you have to integrate that rectangular pulse. So you've got a pulse that's got an amplitude of 4 and goes from 0 to 8. And that, yeah, that's going to become frequency modulation. So, well, it becomes just a ramp. I mean, it gets integrated in here, and then it just hangs at that value. That's what that's going to be. And so this is at 8. And so what is that hang value? It's going to be the area, right? So that would be 32. But then it gets multiplied by the deviation constant, which is 20 hertz per volt. And then it gets multiplied by 2 pi. So when it gets all built up like that, this value that it settles out to is actually 2 pi times 20 times 32.
Where did the
That's the deviation constant.
Oh, the deviation.
Yeah, this guy is FD, that's part of the modulator. And that's in the problem statement.
Yep.
You can't plot a Bessel function spectrum for this. This is actually a pulse type FM, so it's a little bit more complicated spectrum, but you can get the peak frequency deviation, which is 80 hertz peak deviation.
So that could be one.
That could be a calculation. The power in the signal, regardless of what's going on inside the phase or the frequency, is still just a squared over 2. So, I'll probably ask you that question because I'm looking for you to be confusing this between AM and PM or FM. This is constant. It never changes. It doesn't matter what the message is doing. Unless it's an extreme modulation, which I said was impractical, one that would be so wide that it would cross down through DC. This is another kind of classical problem. This is more along the lines of what we've already been talking about. Given a carrier frequency, a deviation, a message, it's FM, so you have to calculate the peak deviation, calculate beta, and the spectrum got plotted here, but you could find out what the bandwidth is based on what we just did. We could say, if we wanted to work from this and say, what is the bandwidth? If beta was equal to 7, the bandwidth is going to be 2 times 7 plus 1 times whatever the tone frequency is. And the tone frequency here is 2 kilohertz. No, that's the carrier. The tone frequency is 10. So you just have to plug that in out here. So that's 15, or 16, I mean. So it's 160 kilohertz. Did I do that right? 10 hertz. No, it's not kilohertz, it's hertz.
Just hertz.
Yeah.
It was just 10, is that right?
Yeah, that's right.
Oh. Yeah.
So you can just look at this one as another rather similar one, except this one goes through calculations and then this one gets into a bandwidth calculation of contained bandwidth. So there's the power calculation right here. And this one was special. There was no power at the carrier, I believe. Well, actually there was. Here's the power in the carrier, and then there's 2s on each of these 3. So this had 3 sidebands on either side. What I haven't shown you is how to get plots like this using MATLAB or Mathematica or whatever, but we plain ran out of time. But I think there's plenty of ideas for you to study over from this one solution set, which is now posted.